Oh, okay. Okay. So let me get started by doing some introduction here. So today our speaker is Golan Bel from Ben Gurion University. That
Ben
sounds right.
Gurion. Ben Gurion was the first prime minister of Israel, so the university is
Okay.
named after him.
Okay. Ben Gurion University, and Golan got his PhD from Israel, and then we met him. I met him at University of California, Santa Barbara. We were doing postdoc there, and then after that, he did postdoc at Los Alamos for a couple of years before he joined faculty at Ben Gurion University from Israel. So today he's going to talk about climate predictions using learning algorithms. Okay, go ahead.
Okay, thank you very much, Rui, for the invitation. And I'm sorry, I apologize for everyone that this is not the usual hour of your seminar, but it's 10 p.m. here, so I wanted to make sure that I will be awake while I'm giving the talk and it won't be midnight. Um, so yeah, as the title says, I will talk about climate predictions. It may sound a little weird that physicists are dealing with climate predictions and learning algorithms, but I hope that I will manage to convince you that there is a good reason to do it, and there are actually many interesting physics questions behind those things. So before I start talking, I want to mention that most of the work that I will present here today was done by myself and former PhD student and postdoc Ehud Strobach. Ehud was until 2 weeks ago, he was a postdoc at NASA in Maryland, and 2 weeks ago he started some staff position in a research institute in Israel. So climate prediction. I like to start with a quote. A Danish proverb says that it's difficult to make predictions, especially about the future. Many people attribute it to Niels Bohr, but apparently it's older than Niels Bohr. And the reason that it is difficult to make a prediction, especially climate predictions, is that climate models, while they're the main tool that we have for climate predictions, the climate system itself is very complex. It includes many, many different spatial and temporal scales. And that's why it is very difficult to capture all the different components of those systems. And that's what makes it also very difficult to make predictions about the system. And that, of course, on top of the nonlinear nature of the system, where we have many different coupled components in nonlinear way. And I hope to give you some flavor of what the complexity of these systems are. So again, in climate prediction, when we talk about climate predictions, then we can ask many different questions. The common question, let's say in the popular media, people like to talk about global warming. So when people talk about global warming, what they're actually interested in is the response of the system to some forcing in terms of the greenhouse gas concentration or CO2 concentration in the atmosphere specifically. And also, but again, the questions can be very different. They can be, for example, how the probability of specific extreme events change, or what would happen to hurricanes, for example, under double CO2 concentration, and many other different questions that you can imagine. And again, different questions are related to different scales, both temporal and spatial scales. So climate models, I adopted this cartoon here, includes, as I said, many different components. Obviously, we have the atmosphere. In the atmosphere, we have the clouds. Uh, we have the land, and the land has different types of land use. I mean, we have some snowy areas, we have some forests, there are some agricultural fields, of course, there are urban areas, and and there are, of course, the oceans. And the oceans themselves are complicated because the depth of the ocean varies between different places. There are the boundary conditions of the coastlines, and all this system, at the end of the day, is driven mostly by the sun. So it's mostly the radiative forcing of the sun that drives the system. In other planets, there are many other interesting effects that drive the local climate system. There are, like, for example, geothermal activity or volcanic activity, and also in some, like in Europa, for example, they have the planet, this moon of Jupiter. It has a magnetic core, a metal core that is affected actually by magnetic forces during its orbit, and that caused some kind of shrinking and expansion. And this viscosity, this small viscosity, very small movement, is enough to generate heat under the thick ice cover of this planet. So there are many different forces on Earth. The radiative forcing by the sun is the main driving force. So I just want to mention that if you have questions, please try to be like Israelis. Israelis are known to be very aggressive with their questions. So feel free to stop me anytime and ask questions. You don't have to wait to the end of the talk.
Great, great.
Okay. So I just wanted to give some examples, for the complexity. So if we talk about, for example, cloud, so there are many different cloud processes. The clouds, first of all, they reflect some of the incoming radiation from the sun. We know that when we have thick clouds, we get some shading by the cloud because they reflect some of the light. Other part of the light is actually transmitted through the cloud. On the other hand, when we have the long wave radiation emitted from the Earth, then this long wave radiation is reflected back, and then we get what we call the greenhouse effect by the clouds. So short wave radiation is passing through the clouds, but when it is emitted as a long wave radiation from the Earth, it gets trapped. Then, of course, the net effects of the clouds depends on many different parameters of the clouds, on the location, the density of the clouds, the thickness, how many clouds are above the specific clouds that we are interested in, and many other factors. But then, again, we have to remember that nucleation of a cloud is something that takes place at the scale of a micron. We start with some dust grain or some other aerosol that is very small, and that is necessary for the nucleation of the cloud. But then once it grows, and it can get to the scale of kilometers. And of course, the dynamic of the clouds take place is affected by synoptic systems, and sometimes synoptic systems have the scale of hundreds or thousands of kilometers. So we have many different spatial and temporal scales involved in clouds alone. Again, if we also want to look at the atmospheric processes, then again, we have many different processes that are all related to the dynamic of the atmosphere. We have, of course, the wind. We have the convection, where hot air goes up and cooler air comes down because the temperature affects the density. Of course, we have effect of the boundary layer. So we have the topography of the soil. We have mountains, and all this affects the flow of the air. And we also have heat exchange and humidity, moisture exchange. So, and all these effects also cause turbulent flow, especially close to the boundary. And it's very difficult to resolve this turbulent flow, especially when we try to simulate the entire Earth, the entire climate system of Earth. not just locally, then it's impossible to resolve, this very small spatial scales. So one example to show another aspect of this complexity, if we talk about atmospheric convection that I mentioned earlier, then one of the famous models known in this context is actually the Lorentz model. And the Lorentz model consists of three ordinary differential equations that seem to be very simple. They are actually derived from partial differential equations that describe the Rayleigh-Bernard convection. Basically what happens to a two-dimensional layer of fluid that is heated from below and cooled from above. So we get this convective flow, but if we try to follow, and there are here different parameters, I mean, the variables that we have here, one of them is actually proportional to the rate of the convection. It related to the stream function. And there are two other variables that are related to the temperature dynamic. And there are three constants that dictate basically the type of dynamics that can be observed in this simple model. And these parameters, they depend on the fluid itself. I mean, they of course vary between water and air, and also the physical dimension of the system itself. So the model is well known for its chaotic dynamics. So basically what you can see here is just a case where we have two trajectories, and you can see that they start really close to each other. I mean, in this scale, we cannot even see any difference between them. They start together, but then as the system evolves, the dynamic evolves, the two trajectories are becoming very different. And basically each of these trajectories actually is hopping between two different attractors, but it is basically impossible to predict how long each of these trajectories will spend in each attractor before it jumps to the other one. And that's why as the system evolves, we get very different dynamics. So this sensitivity to initial condition or chaotic dynamic, which is also part of the atmospheric dynamic, add of course to the complexity, because then it means that we never know the exact state of the system to initiate it. And if the result we get is sensitive to the initial conditions, then we're in trouble, because then how can we make prediction about anything in the future? Is that okay? Everything clear?
Good. I think everything's good. Yeah.
Okay. Okay, so the models also, what the models do in order to deal with all the processes that are not directly resolved is something that is called parametrization. And parametrization basically means that I mentioned earlier all the complexity of clouds. So if you look at all the complexity of clouds, then you get different type of clouds, different shapes, different thickness, and so on. And what the model does is that at the end of the day, it is trying to follow only two variables, which are the air temperature and the relative humidity. And based on these two parameters, to assign to each grid cell, to each position in space, what fraction of the space is covered by clouds. And what is the composition of the droplet sizes. This is important for the scattering of light. So for the scattering of the radiation. Okay, so they take basically all these complicated processes that I mentioned earlier, and they try to replace them by some kind of effective model. It's very common in physics. I mean, in physics, we always do it. We try to take some complicated system and find some effective, simple, or relatively simple, effective model to describe it using as few degrees of freedom as possible. So similar thing is happen here, but different models use different ways to do it. And that's why there are differences between different models. Not all the models do this step of taking the full process or all the different components and trying to translate them into effective model in the same way. So there are different groups. Usually the groups are based on locations in the world. And different groups do this parameterization differently. Similar thing happened here. This is just another example with a land surface model. So as you may know, the dynamic of water in the soil is very complicated because the soil is a porous medium. So the dynamic is quite complicated and it's very difficult to predict, or there is no accurate model for the evapotranspiration from a given area, given place, I mean, with specific plants. And there are different effective models. And all these things, at the end of the day, goes into usually very, very simplified models. The common one, which is kind of state of the art nowadays, is modeled with only 4 layers in the soil. And the dynamic between the different layers is kind of simple, like one layer gets full and then it overflows to the layer below it and so on. Something that is far from the real nature of the dynamic. And of course, it completely ignored all the specific details of the plants. So all the plants are basically replaced by forest, bush, and some other grass. And that's all. So there is no reference to the specific behavior in specific regions. And again, different groups do this process of simplifying differently. And of course, the different simplifications affect the dynamic. So after, I hope that you got the complexity involved in these models and the different issues that modelers have to deal with when they design a climate model. And if we try now to look at the predictions of the model. So in this case, this figure is taken from the IPCC report. It shows basically the spread of the predictions of 114 models, which were at the time the state-of-the-art models. And it took their predictions for different periods. Okay, so for example, here they took the heating, the warming rate in Celsius degrees per decade. Okay, and then they compared it to the actual observation. So as you can see, even in the observation, it is not a single point, right? I mean, it should be, if it is an exact observation, it should be a single point. But of course, we don't have an observation at every point on Earth. So the way to do it is to take all the available measurements from satellites, from stations on Earth, and from buoys in the ocean. And at the end of the day, to combine all this data, doing something that is called reanalysis. And this reanalysis generates some kind of a global map of the temperature, and then they average over it, and they get the globally average temperature. And from this quantity, they derive the warming rate. Okay, so you can see here, the x-axis is basically the warming rate in Celsius degrees per decade. And the histogram shows the distribution of the predictions of different models, of all the models in the ensemble, in this case, 114. And the dashed area, the dashed red area, this shows the actual measurement.
So this is about global warming, right? You're talking about global warming.
Yeah,
Basically.
in this case, it is about global warming. The IPCC, is mostly focused on global warming.
Okay.
But what you can see here is something, uh, I don't know if surprising, but you can see that between 1984 and 1998, the measured warming was actually much higher than most models predicted. Right? I mean, most of the models are to the left of the actual measurement. But then if you go to 1998 to 2012, then you can see that actually most models overpredicted the warming. Actually, this period is known as a high-out. Basically, since 1998 until 2 or 3 years ago, the claimed global warming actually stopped. And there is still no clear explanation why it happened, why it stopped. Because, of course, the emission of CO2 has not declined.
This is very different from what we heard from news, I guess.
I'm sorry?
You're saying basically from 1998 to 2012 is pretty much stopped, right? The warming.
Yeah, I mean, even later, I mean, until 2017, I think they claim that in 2017 it started warming again. But there was, a period of almost 20 years during which they haven't measured any warming, at least not in the, they did measure in specific locations, but not on global average.
Mm-hmm.
Yeah. So again, if we go back to a longer period from 1951 to 2012, then you can see that basically the average, over most of the models, I mean, the distribution is much narrower and pretty much in agreement with the measurements. But that should not surprise you because basically all these models that I mentioned, so basically each of these models has thousands of constants. And very few of them are actually, precisely known. So many of them are basically tuned in order to fit the global average temperature. That is the main thing that is used actually to tune the models. And because this period that is considered here is exactly the same period that is used to tune the models, then it is not surprising that they're in good agreement. Okay, so that's why here you can see a better agreement. So I just want to mention that now, if you go back to these to the two left panels, what you can see is, of course, that during different periods, different models performed better. Okay, the models that contributed, for example, to this column are not the same models that contributed to this one. Okay, so different models perform differently in different periods and also at different locations, as we will see later. Okay, now the next thing about climate prediction is, of course, the associated uncertainty. So again, because different models have different prediction, then in this case, if you look at the projection of the model, then this part is a historical part. And then when it goes into the future, you can see that the uncertainty basically grows. The spread here represents basically the spread of model prediction. And the reason that the spread is growing, there are basically three main factors that contribute to this spread, or basically to the uncertainty. One of them is what I mentioned, is the difference between the different models. Another one is the sensitivity to initial condition. Okay, unfortunately, among the climate community, the sensitivity to initial condition is something that is known as a natural variability, because they believe that this sensitivity is the natural variability of the climate system. But of course it is not. It's basically the sensitivity of the model to initial conditions. It's we don't know for sure that it has anything to do with the real climate system. And then the third thing, which is dominating actually the long range prediction, is the emission uncertainty. We don't know what will be the atmospheric composition in the future, because we don't know what will be the CO2 concentration, and according to the temperature, we don't know also what will be the water concentration. Water, by the way, is the main greenhouse gas in the atmosphere. So when you look at this thing, I mean, what you can see here is that, you know, at short term, the main contribution to the uncertainty comes from the sensitivity to initial condition and the difference between different models. But then when you go to the long range, the main contribution comes from the emission uncertainty. Okay, and you can see it clearly here where they separate two different, they call them RCP, okay, which is a representative common pathway for they took, you know, several scenarios for the concentration of CO2. And according to this scenario, they ran the model. Basically, they force a model by a given concentration in the future, and then they look at what would happen. So the two different shaded areas here correspond to two different scenarios. One of them, the lower one, is the most conservative one, which says that basically the concentration of CO2 will not grow. It will remain as it is today. And the 8.5, the RCP 8.5 is the most radical one that says that it is going to grow very rapidly because, for example, China and India are going to start emitting in a similar rate as the US. So you can see that the main difference becomes actually between the two different RCPs, but only in long term. In short term, okay, and short term means, you know, several decades, a few decades, the main uncertainty comes from the model variability, the difference between models, and the internal variability, basically the sensitivity of each of the models to initial condition.
So, okay. So based on your statement, it seems like human has a very big impact on this, right? Because the emission uncertainty could give you very different results. Like yes. on the so human does have a pretty significant impact, right, to whatever.
So, you know, it's not directly human because it's basically what they do is that they look at the CO2 concentration. Mm-hmm. Okay, what they assign is the CO2 concentration. And it is unclear, you know, many studies that looked into the correlation between CO2 and between CO2 and temperature actually showed that, you know, when the temperature grows up, the CO2 concentration goes up and not vice versa. Mm-hmm. Okay, so it's unknown what is the cause and what is the response. And also, if you increase the emission, I mean, you have to take into account also the ability of the climate system of the Earth to absorb, because the ocean absorbs a lot of the CO2. And the question is, what happens when you increase the emission? Would you also increase the absorption, or would it all remain in the atmosphere? Mm-hmm. Okay, and so all these things are not known. That's why, you know, it is better, I think, to look at it in a way that, yeah, if you set the CO2 concentration in the atmosphere, it has a very serious impact, very strong effect. Uh-huh. Okay, so to say human, I would be more careful about that.
I see, yeah.
Okay. Okay, so the first thing we did is that, you know, we wanted to look into what happened with decadal prediction. So I want to go back to this slide and mention that there are two types of climate predictions, mostly two types. One of them is called projections, and that's basically the kind of predictions for the long future, far future. Basically goes, you see, to 2100. So it's basically, 100 years ahead prediction. Um, and when people do this kind of projections, they actually mostly look into the response of the system to forcing. Okay, as you can see in these two scenarios. But there is a different kind of climate predictions that became actually quite focus of many research, and that is decadal prediction. Decadal predictions are predictions for something which is between 10 to 30 years. And the reason that people do it is because they found that when they do this kind of prediction, they actually initialize them with the observed conditions. So they take the reanalysis data that I mentioned earlier, and they use it to set the initial condition at a specific time. And then they simulate the system for up to 30 years. And once they do it, they found that this kind of predictions actually can have skill in some places. So it is useful in some places, and it's something that they could also test about the past. Unlike projections for scenarios, with a double CO2 or more than double CO2, that this is something they cannot test. So that's why people do it. And this is the kind of predictions that my research focused on. Because I thought that this kind of prediction is actually more interesting, and that's where I expect the models actually to have a little more power or predictive power. So the first thing we did was to try and decompose the variability of the ensemble. So we considered an ensemble of different models, and each of the models had several initial conditions. Basically, when I say several initial conditions, what I mean is that if they started it, for example, in December 1980, then they take the model and they start it in different days in that month. Okay, and as I mentioned earlier, because we have some chaotic dynamics, and when you start at different days, even when you go 20 years ahead, the results are slightly different. The paths that you get, the trajectories of the climate system that you get are slightly different. And of course, the trajectories of different models are different. Okay, so what we did is that we took, basically we said that the total variability, the total shaded area that I showed you earlier, actually has different contributions. And then you can break, you can show analytically that you can break the total variability into the sum of two terms, one of them representing the internal variability, basically the sensitivity of the models to the initial condition, and the other one represents the differences between the different models because of different parameterizations, different grids that they use, different numerical schemes, and so on. Okay.
So I bet a lot of students get lost on this slide. So let me try to summarize. So what you guys doing is you're not proposing a new model, but you're actually taking the given models, right? You're kind of like doing an average of all the models, try to get something out of it, right? That
yeah. So what I want to do, basically, I will come to the idea in a second, but what I want to say is that, first of all, I want to understand how important is the difference between different models versus the differences between different initial conditions of the same model. And why I want to understand it. The reason I want to understand it is because if the difference between different models is larger than the difference between different initial conditions of each model, then it makes sense to try and understand, which model is better. Okay. Yeah. But if the sensitivity to initial condition of each model is larger, is the main factor that contribute to the uncertainty, then there is nothing I can do about it, right? I mean, how can I tell you that it is better to start on December 1st versus December 5th? I mean, it makes no sense, right? I mean, if this is my model, then basically what I say is that, the model is useless. So that's why I want, first of all, to try and understand, what contribute to the variability when I take an ensemble that has different models and different initial conditions for each model. I want to understand what dominates the variability, what
Mhm.
leads to the uncertainty.
Mhm.
Okay, I hope that the point is clear.
Yeah, yeah, I think so. Yeah.
Okay. Okay, so another point that you have to be aware of, I know there is a lot of text on this slide, but you don't have to read it all. I just want you to understand that in a slide like the one I showed you, for example, here, and I showed you the predicted warming per decade, right?
Hmm.
And the warming per decade is something that, of course, is not related to the actual temperature, right? It's only related to the change in temperature.
Right. Yeah.
And the reason is that, most of the climate models are actually incapable of reproducing current day condition.
Mhm.
So, for example, most of the models, what they do is that they simulate Earth that is warmer by several Celsius degrees or colder by several Celsius degrees. But somehow the people in the community convince themselves that while the temperature itself is not accurate, they can actually consider very seriously the dynamics, the difference, the fluctuations around the wrong mean value. Okay, so I personally, you can probably hear it by my tone, I'm very critical of this attitude because I believe that if the first moment, the mean state is not predicted correctly, why should I believe higher moments? Why should I believe the fluctuations around it?
Right.
But anyway, this is a common thing in the field, and there are people in that field that are much smarter than me, and they all follow this methodology. So I have to consider it. And I just want to mention that when one comes to analyze the result of any ensemble of climate predictions, climate model, one has to decide what anomaly to consider. So for example, whether we consider the difference from some kind of average from observation or the difference from the mean state of the specific um, model or anything else. Okay, I can tell you that several works in the last decade already pointed out, including our work, pointed out that the results that you get and the conclusion depends on how you define the anomaly. Okay, so this is something to take into account. So because of my more conservative attitude to this issue, what we did is that we considered some kind of anomaly that is the simplest possible in my opinion, and that's that we just subtracted from each model the climatology, okay, uh, from of the observation. So when I say climatology of the observation, what I mean is that we considered, for example, the last 30 years. Okay, in the last 30 years, we calculated the average annual cycle. For example, the average temperature in January, okay, in a specific location. And then we took the prediction of the model for that specific month and we subtract this 30-year average of observation from that prediction. So in this way, we don't actually correct the bias of different models, but we just, we set the zero at a different place. And we do it separately for different months because we have to take into account the annual cycle, basically, of the season in different places. Okay, and in order to get the average of the observation, then we consider the reanalysis data. That's what I mentioned earlier, some kind of interpolation of all the observation in order to get a continuous grid that covers the Earth and gives the temperature or any other variable at different locations at each month of each year in the past. Okay, so if we look now at the ensemble that we considered of models, and we look here at two different variables. So we looked at the average global temperature and the average global zonal wind. Zonal means east to west. Okay, so if we look at this at these two variables, we can see that different models have very different prediction. Okay, and not just that the prediction is different, you can also see that the slope is different. So all the models agree that, I mean, they all predict somewhat warming, maybe except for one of them, the blue one shown here. Okay, that shows actually some kind of a decrease of the average global temperature and then a very slight increase. But all the others show overall warming. And of course, there is no obvious trend for the wind, for the zonal wind, but the values themselves are very different between the different models. So as you can see, they all have some fluctuations. I mean, one would naively expect that the fluctuations would be around zero because of the global average, but this is not exactly around zero. Okay, then when we try to understand what is the variability and depending on the averaging periods, and we have averaging period that varies from 1 month to 1 year. And what we can see is basically that as we increase the averaging period, so if I ask what is the annual average temperature, then the variability of the ensemble is smaller than if I ask what is the average monthly temperature. That's because different models disagree about the temperature, let's say the amplitude of the annual cycle, right? I mean, what would be the difference between the colder month and the warmest month of the year? So if I do an annual average, this difference in amplitude is averaged out. Okay, while if I consider monthly averages, then it also contributes to the variability, to the difference between the different models. Moreover, the different models, of course, they disagree with the timing. What would be the coldest month, for example? Would it be January or February? Okay, and these differences, of course, also contribute to the total variability. But what you can see is that in almost all, no matter what average period we use here, we still get that the model variability is significant, is a significant portion of the total variability for both temperature and zonal wind.
Mm-hmm.
Okay, then if we look at global, if we want to look at the spatial distribution of the variability for these two variables, the surface temperature and the zonal wind, then what we can see is that it varies a lot between different locations. Right? I mean, what we can immediately see that for the surface temperature, the variability is larger, okay, over land compared with over the ocean. Okay, and for the zonal wind, it is actually the opposite. Okay, the variability is actually higher over the oceans. So we wanted to understand why, and the first thing that we did is to look into the cross correlation between the variability of the surface temperature and the topography or the elevation. And what we found is that the correlation between these two variables is actually quite high, which means that in areas with higher elevation, where usually the topography is more complicated, then we have a larger disagreement between the models. And that's why we have a larger variability. Okay, we also found that there is a very strong correlation actually with sea ice and snow cover. So if we focus on regions that are covered with either snow or ice some part of the year, then these are actually the locations where we have the largest disagreement between different models and different initial conditions, because the extent of the sea ice, for example, varies between different models and also the timing of it. So that's why we get higher variability in areas where we have sea ice or snow cover. Uh, for the zonal wind, what we actually found is that the large variability, or the variability is highly correlated to the average zonal wind in that location. So the stronger the wind in a specific position, the larger is the variability, or the larger is the disagreement between the model. Okay, and that kind of makes sense, right? I mean, because overall what we get is that the coefficient of variation, which is kind of characterizing, how broad the distribution of values that we get is not actually, it doesn't change much. But of course, when the mean is at a higher value, then also the spread is a bit larger. So overall, we found that when we try to take now in this analysis and look what is the contribution in different regions of the model variability out of the total variability that we have in the ensemble, then what we found is that almost everywhere, for surface temperature, almost everywhere, the model variability dominates. And even for the zonal wind, in most locations, the model variability is quite significant. And this results basically, I will skip a little bit, I will skip a few slides here, and I will go to the summary of this part of variability analysis. And basically, what we found is that model variability is significant everywhere. And so if we can do anything to reduce it, we might actually get better prediction, right? I mean, with smaller uncertainty. And that brings me basically to the main idea. So that kind of justified our motivation to do what we did, where we study the performance of different models in the next part of the talk that I'm going to show you. So if you have any questions about the variability, just let me know. And if not, then I will move to talk about the learning algorithms and the idea behind them.
So basically, I guess your point is like, because the model variability is the main factor, right? So it makes sense to build a better model, right? This is basically
exactly.
Okay. Yeah. Okay. Yeah. I guess you have to be a little bit quick, fast on doing the main part.
Okay.
Go ahead. Yeah.
Okay. So I want to stress again the logic behind the use of learning algorithm. And the logic is that, if we weight the ensemble members, basically if we weight the different models, okay, then of course we reduce the uncertainty, right? Because bad models will get a much smaller weight.
Mm-hmm.
So we don't have to consider them as we consider the good models.
Mm-hmm.
So then our predictions will have a much smaller uncertainties associated with them.
Mm-hmm.
And of course, once we do it, we might also improve the predictions themselves, because the prediction itself will be basically mostly based on good models, not on bad ones.
My question is, why can't we just choose one model?
What is a good model?
Z model, yeah, the actual model, or like just like in a lot of branch of physics, right? We normally just have one fundamental theory. We'll just take that theory instead of taking average of a bunch of different theories,
Yes, but basically, so in my opinion, a good model, if you are trying to predict temperatures, then a good model is a model that predict the temperature good in the past, right?
Mm-hmm.
So for example, I run it now in the past. If it managed to predict well the past conditions that I already observed,
Mm-hmm.
so it agrees with my experiments,
Mm-hmm.
and then it is a good model. But
Mm-hmm.
if it cannot predict the past well,
Mm-hmm.
then I know for sure that it is a bad model.
Right.
So you can tell me, of course, that the fact that the model was good in predicting the past does not guarantee that it will be good in predicting the future.
Right.
But this is the best I have.
Right.
Right? I mean, I don't have any other information. That's the only information. The climate system has only one realization. I don't have an ensemble of climate system.
Exactly. Yeah.
Okay. Yeah. So there are several advantages to use. You can imagine giving weights, using different functions. So why to go and use learning algorithms in order to weight them?
Mm-hmm.
There are several advantages to the learning algorithm. One of them, and maybe the main one, is that there is no assumption regarding the distribution. Unlike Bayesian theorem and many other theorems that are commonly used, we don't assume that the errors are Gaussianly distributed or anything like that.
Mm-hmm.
We just have no assumption about the prediction or about the errors.
Mm-hmm.
And that's why we can apply it to any variable of interest. It can be the temperature, it can be the wind, it can be the surface pressure, anything you want. The second thing is that we can prove mathematically, okay, that there is an upper bound to the error, or if you want, to the deviation of our predictions relative to the best model in the ensemble.
Mm-hmm.
So when you consider an ensemble of models and you just consider their average, you might be worse than the best model, right? I mean, because you also consider the bad model.
Mm-hmm.
But when you use the learning algorithms, then you have guarantees that if you learn for long enough, you will be at least as good as the best model in the ensemble.
Mm-hmm.
And the last thing is that the motivation to use sequential learning algorithm is actually that we can update the weights of each model in each grid point with a very low computational cost. So it's something that we can do it, we can run on real time, and every time we get a new measurement, we can update the weights and make prediction for the next step.
Mm-hmm.
Okay, so again, we assign weights to the climate models, okay, based on their performance, okay? And then our prediction is basically the weighted average of the ensemble. So we take the prediction of each model, multiplied by the weight assigned to this model, and this way we make prediction for the future. Okay, and we do it for each grid cell separately. So we consider three different learning algorithms. The three different learning algorithms are, they are called EWA, LAA, and EGA. I won't bother you here with all the full mathematical details of this, but I want to give you the essence of the difference between them. So the LAA and the EWA, they both follow the best model. Mm-hmm. So if you learn for long enough, you will converge to the best model, except for the fact that the LAA always makes sure to keep all the models in the ensemble contributing something. Mm. So if you have a very bad model, it won't get a zero weight, but it will get some very low weight. And that's basically in order to make sure that if your data or if your system is not stationary, and maybe in the past the model was bad, but in the future it will become good, it will be possible for it to immediately get higher weight when it starts performing well. Mm-hmm. The EWA doesn't do it, and it just basically follows the best model. The EGA, on the other hand, is actually looking into the mutual information between the model, the prediction of the model, and the observation, and basically into the mutual entropy, if you want. If anyone is interested, you are more than welcome to look up the paper and see the details, the mathematical details of the algorithm. But the bottom line is that it follows the actual observation. In this plot, what I show you is just a very simple experiment. I'm trying to illustrate the idea. So we have basically two predictions. Okay, one prediction is always 1. The other prediction is always 0. The green and the red dotted lines. Okay, the real measurement is also constant, okay, and it is here at 0.7. So when we start, basically we give the same weight to the two experts. Okay, so the expert saying 1 and the expert saying 0, they both get the same weight. Okay, but then as we start learning, then you can see that the two models that follow the best expert converge to 1 because it is closer to the prediction. But EGA converge actually to the real value. Okay, so it converts to the real value by giving some weight to experts that says 1 and some weight to the expert that says 0, and combining their predictions such that it gets as close as possible to the real value. Again, there is the different learning algorithms have different performance. I mean, what we did in this experiment is that at some point we switched the predictions of the two experts. So when we switch the predictions of the two experts, now the models have to reassign the weights. Okay, so in the first part, it is what you saw earlier. Okay, and then they converged. But then here at this point, we switch the expert. So now they have to reassign the weights. And what you can see is that basically there is a difference in how quickly they learn that things have changed. And once they learn, then again, they converge each of them to the corresponding weight. Okay, so I have to finish, but I will just say that when we try to measure the performance, what we looked at is the root mean squared error between the prediction and the actual measurement. So we used some period in order to learn the performance and assign weights, and then we stopped the learning. Okay, and once we stop the learning, then the weights are fixed. And then we make prediction for the future. And then we test. We test how good our predictions are. Okay, so when we do it, I'm skipping here. I just want to show you here. Then we use different learning periods. So we have 30 years of simulation. Okay, and we use different learning periods. I mean, this group, for example, correspond to learning 5 years and predicting 25 years. Okay, then this group learning 10 years, predicting 20, and so on. And you can see that when we learn only for a short time, then the performance is of most of the error basically, you know, is not much better than the error of the climatology. The climatology basically says that, you know, we will consider the null model. We will say that what happened in the past will happen in the future, right? I mean, if I ask you to give me a weather prediction for tomorrow and you know nothing, then your zero guess will be that the weather will be the same as it was today. And most of the time you will do well. So that basically, when I show here a climatology, this orange column, then what it shows you here that this outperforms, okay, for example, regression that try to combine the different models and also some of the other learning algorithms. But as we learn more for longer period, so for example, when we learn for 20 years and only predict for 10 years, okay, then we already can outperform the climatology. And I just want to mention, that will be maybe the last point I mentioned, that it may sound weird to you, but none of the models, even if you consider the state-of-the-art model nowadays, it cannot outperform climatology. Climatology does much, much better. actually our attempt here using learning algorithm is the first time that, combined models could outperform the climatology. And that's only because of the learning algorithms that we used. And we did many tests to that. And at the end, we found that, we need to learn for at least as long as we want to predict for. Okay, but then we cannot learn for too long, because if we learn for too long or if we predict for too short period, then it might be something that is not representative, and that's why we will not be able to predict it well. Okay, so I think maybe with that it's good for me to stop, and if you have any questions, I will be more than happy to answer.
Yeah, let's first thank our speaker for a wonderful talk. Just showing up like by thumb or virtual class or whatever. Yeah. Yeah, we have time for a couple of quick questions. Anybody have a question? I guess you don't have to raise your hand. Just ask. Go ahead and ask if you have any questions. Maybe I can start from first question. So, Golan, you talk about there. I think seems like there are two kind of difficulties in this kind of problem. One is the nonlinear nature of the system, right? Like this, for something as simple as the Lorenz model, they're right like chaotic behavior and everything. Well, the other one you mentioned is like the multi-scale existence of like spatial and also temporal scales. Well, do you think these two are kind of like these are, I feel like it's kind of separate from each other, right? The nonlinear and the scale, but they're also kind of connected, because the thing is, if it's let's say for example you have some nonlinearity and then chaotic in the shorter time or length scale, but if all the scales are kind of connected, then it would affect your long-term prediction or something. What do you think?
So I don't think that the two are completely unrelated. I mean, it is true that I presented it as two separate things, and there are issues for which the two are separated. But as you know, for example, when you have nonlinear dynamics, for example, in the ocean or in the atmosphere, you can get turbulence. And when you have turbulence, then you basically have a cascade. Energy flows from large scale into small scale in 3 dimensions. Okay, and what it means basically is that if you do not resolve the small scales properly, right? I mean, then the amount of energy that you take out of the system is not the correct one. So you don't represent your system well. And of course, if you would have, infinite resolution, you could predict all scale, you could simulate all scales properly and, describe the turbulence properly.
Yeah.
So I think the two things are, they're related in some aspects, but in other aspects, they might not be the dominant problem or the main problem.
Another question I have is like, based on what you described, it seems like overall, we're not really very successful in terms of any of those predictions. Like out of these 100 or something models, and it seemed like, again, the prediction they gave is really sometimes good, sometimes bad, and it depends on which time scale you're looking at, right? Which period of years you're looking at. It seemed like we're really kind of like really at the preliminary stage in terms of doing this kind of predictions. Is that right?
Yeah, so, I want to ask you guys, and maybe the students can answer. Why are we successful in weather prediction? Right? I mean, if I told you about all these problems in climate prediction, and the climate system is basically the same system that we use, right? I mean, for weather.
Yeah.
So why are we successful in weather forecast, and we are so poor in climate? Anyone with an idea?
Parker, go ahead. Parker, can you answer the question, Parker?
I guess with weather predictions, you can kind of predict where the weather's coming from and where it's going, so you might get a little bit easier rather than just a long-term climate, maybe.
Yeah, but why? You're right that it is easier, but why?
I'm not sure, actually.
Okay, so let me tell you something. Maybe that will be, one thing that you will get from the time I wasted for you today. So basically, the weather is dictated by synoptic system. Synoptic system means, some kind of dynamic of the atmosphere. And the correlation time of synoptic systems is between 7 to 10 days. So that's why we have a very good weather forecast for 7 to 10 days. But once you try to go beyond the correlation time of the synoptic systems, then we have no knowledge, or very poor knowledge. That's why usually you can see that if you would try to make predictions for a month ahead, it will be very poor already. Just because it goes beyond the correlation time. So I just want to mention, yes, the situation with climate is, at least from my perspective, coming from theoretical physics, where you usually, you solve analytically the equations and you get very nice results. And usually, if you plot against some experiment data, then the agreement is, terrific to several percent maybe of error. And coming to the climate, it seemed to me like a total disaster. Really, because it's, as I told you, if climatology is better than any model, then why to waste our time with it?
I agree, yeah.
But I think that at the end of the day, we do learn from these models a lot about, many of the physical processes that are involved in this system. And I'm not sure, that anytime soon we will have much better climate predictions, but hopefully we will learn a little more about the climate system and about geophysical fluid dynamics in general.
Guys, I have another question. I mean, just like the other one is also interesting. Like based on what you have, you don't have time to talk about all the details about your learning algorithm, but seems like you could do the same with like using a machine, like using machine learning or something. Like using certain algorithm, you're doing certain stuff. You can let the machine adjust the weights of different models. And I mean, I don't know whether anybody have done anything like that, but it sounds like a kind of natural direction.
So again, if you do it for models, just in order to learn, so the learning algorithm or machine learning, that is basically, one form of machine learning, what I did.
Okay.
But what I learned is basically the performance of the models, right? I mean, what people are trying to do nowadays is actually to use machine learning instead of models.
Okay.
So what they say, okay, let's take only data, okay? And all this data will go into this black box of deep learning.
Right.
And then we will get as an output prediction. So you can do it. And of course, in many cases, it is very successful. But I think that the main problem with that is that we don't learn anything new about the system. We don't understand nature better if we do it.
It's a black
box. It might be useful from practical point of view, but not from, it won't contribute anything to our attempt to understand those systems.
But I mean, I guess at least we can learn one thing. If the machine can predict something really good, compared with all the models we have, it seems like suggesting there is some underlying like simplicity or some kind of theory that haven't been discovered by us. I mean, right? I mean, if we can get all the predictions right from using like deep learning algorithm or something.
So again, I think that, when I say that the predictions are successful, then usually the predictions for short term are successful.
Yeah.
Predictions for long term are not successful. And the reason is that, the time series or all the variables are not stationary.
Right. Yeah.
Okay, and when the system is not stationary and non-linear, then all these algorithms, the deep learning, they work perfectly, for linear systems. Or for something that you can approximate by many, many linear steps. But once it is inherently, it has some chaotic components, and also, it's inherently nonlinear, the performance is very poor.
Yeah, I know some people want to use deep learning for like a stock treatment. I think stock treating is even more complicated than this system because there are a lot of decision makers and everything. Seems like even crazier. I wouldn't think that it's going to be successful. Yeah, I'm sorry. I have a lot of questions. So you guys have any questions? Go ahead. Anybody want to ask a question? Okay. It seems like they're all like feel like probably a lot of stuff. I mean, I think it's really interesting talk. I learned a lot from it, and I think it's a lot very interesting. And but I guess we're kind of running out of time. So let's thank our speaker again, and then another round of applause, and then I guess I'll just see you guys later, and then Glenn, I'll talk to you later. I really appreciate it. Yeah.
Okay. Thank you, everyone, for your attention.
Thank you.
Yeah, I start recording now.